Hi, in this video, we want to take a look at learning curves with machine learning. All right, so we're going to have two big concepts about learning curves. One is about the amount of data we have and how that it will improve the accuracy of our model. The other one is looking at the complexity of a model and how that affects how well the algorithm learns. All right, so we're going to be taking material from an introduction to data science, a Python approach to concepts, techniques, and applications. Most of the code, I copied and pasted the code from this website and then modified it to make sure it ran on my machine. So here we go. And we can get the textbook for free from the UCF library. I almost said UF, that's where I went to school. All right, so learning curves. So what we want to do, we want to understand about how changing the amount of data we train a model on improves the accuracy, and we want to understand how complexity can help or hinder the accuracy of our model. So let's go ahead and get our packages in. Let's get NumPy, Matplotlib in. And here I'm going to go ahead and say max in is equal to 700. And what we want to do, let's take a look at this plot. Let's say that this is my data. What I have is my goal is to classify the color of each dot with a learning algorithm. So we can see that if we have like far to the left and far to the right, it's red. If we have down low, it tends to be red, not 100%. And so what we want to do, we want to use the, this predictor variable and this predictor variable to classify red or blue. Now, one thing you'll notice about this is that here I've got red and blue overlapping. So this is an important aspect about predictive modeling. When the region that it overlaps here, so I've got red and blue here. Actually, if you look, I've got some red and blue in there also. So what will happen is really no matter what I do, no matter what I try, where I've got like a lot of overlap, I'm gonna have errors. There's nothing I can do. I can see in the regions where it's almost all blue and there's a few reds in there, then it's gonna be calling blue and all those reds are gonna be wrong. And when I have a lot of reds and just a speckled few blues, the model's gonna probably call red, and it's going to be wrong every time it's a blue. There's a limit to how accurate my model can be. So the data only supports a certain level of accuracy. Now, if I had a third variable in there, maybe a fourth, a fifth, a sixth, I might be able to improve this. But inherently, no matter what I do, I can only achieve a certain level of accuracy. And my goal is to get the best accuracy possible. And when I talk about making a prediction on the future, I have to tell the decision makers that there are limits to this model and it can only get so good. All right, so let's go ahead and get some more packages. Let's get some sklearn going. So we're going to get metrics and tree because we're going to be using decision trees, and we're using metrics to evaluate our model. All right, so what we want to do, we want to go ahead and we're going to set our complexity parameter to 5, and we're going to set the maximum into 1,000. And we're going to have a train set and a test set. So if I look here, this is how I'm going to be storing my test data. And this is going to be how I'm going to be storing my training data. So you'll notice that since I'm generating it, what I've done is I've gone through and I have like placeholders in position to hold my data. And then I'm going to go in and I'm going to start putting in the values, because this is a random number generator model. This isn't a real model, but the reason why I'm choosing this is because here we can make a good picture to represent what's going on. All right, so what we're going to do is we're going to go through this several times, and we want to get a feel for how accurate we can get our model. All right, so if I look through here, what we're doing, we're taking, like this code is we're generating our predictor variables. Here is my target variable. I am permuting the data, and then I'm partitioning, or then I'm randomly sorting the data up to make sure that there's no hidden trends in my data at all. Then we split up the data into test and train. And here is the training set. So you'll notice that we're taking values from X to get our test set. So, and we're taking our values from Y to be our target variable. And then we're going to take a decision tree classifier, and the max depth is C. All right, so how this is going to work is we've got a node for our decision tree, then it's going to split, then it's going to split again, and it's going to split. And 5 tells it how deep those splittings will go. So let's go ahead and do this. And I'm running through this 10 different times. Takes a little bit. All right, there we go. All right, so let's take a look at what we generated on the last iteration. So there are the predictor variables. There's the target variables. And here we've got 1 and -1 coding to correspond to the different colors. X test is just a smaller array. It's a subset of the original X. We have Y test, subset of the Ys. And then we have XR, which is our training data. YR is our target variable for the training data. So on this line, we're saying that we're making CLF as a decision tree classifier. Here we're fitting it on the X training data and the Y training data. And then here on this line is we're checking to see the accuracy for the values on our test set. Here we're taking the accuracy of it on our training set. So remember that almost always the metrics on our training data is going to be better than the metrics on our test data. If I don't have it that way, there's probably an outlier in my data. Now, this data is randomly generated, so I know that there's not going to be any weird outlier things going out. Even if there was an outlier in this situation, I would consider it just part of the population because I know how the data was generated. All right, so now let's go ahead and let's visualize this. I want you to see something very particular about this. Okay, so what we've got here is that we've got this graph, and we can see this is the number of samples that we have. So this is sample size, and here's the error rate. Okay, so let's look at our training data. So as the sample size got bigger, the accuracy of the training data got better and better and better. And the accuracy of the predictions on the test set got better, better, and better. So you can see that when I have very little data, I can't really fit a model very well. You see that on my test sets, it hasn't really, when I have very few data points, the model doesn't have enough to work with. It can't really detect what's going on. As I get more and more data in there, what's going on is that this line represents, this like weird wiggly line represents how well the sample is or how well the model understands the population. And this line, you can think of it as, this is how well the model understands the data. So remember, whenever we're doing machine learning, we want to know about the population, but what I have to work with is a sample. All right. If I knew everything about the population, I wouldn't be doing statistics. I wouldn't be doing machine learning. All right, so our data is our surrogate of what's really going on. So if I go out and I collect it, let's say the height of people, I go and I start measuring the height of people. What I want to know is, what is the true distribution of heights in the United States? What I'm gonna have is some data about the heights of people in the United States. There is a difference. I don't have the complete picture. What I do, I want to sample until I have a good enough of a picture. Well, in real life, your sample may be maybe a good representation, it may be a bad representation, and you don't really know until you start digging in. All right, so here, you'll notice that when I have very low data, there's a big gap. All right, so whenever you see a big gap in your metrics on your train and test set, that is an indication that your model is fitted to the data, not to the population. Now notice also, it gets closer and closer and closer. So the more data that we start putting in, the more that the sample looks like the actual population. And since it looks more like the population, the model is fitting closer to what the true population is. But you'll notice that there is a gap. No matter what we do, there's a gap. And I mean, so I guess if we had infinite size data points, that gap would probably get super, super small. But you'll notice, as this gets to be horizontal, the error rate, what's like the best error rate I could possibly hope for? I mean, this is what, maybe 11% error rate, something like that, 12%. I'm just eyeballing the numbers. If you disagree, I'm gonna put a comment in the YouTube video. I don't care. So you can see that no matter what I do with this model, the data and the model structure together can only produce a certain level of accuracy, and that's it. There's only so good it can get. And this is something that you should always be mindful about when you're doing modeling. I've had the experience in work where I absolutely must achieve like let's say a 90% accuracy, and I'm only getting 80% or 75% accuracy. And I spend a week of my life like focused on fitting models, trying different models. And in the end, it just wasn't in the data. There's just only so good that you can get out of it with the variables that you have. And in that situation, the only thing you can really do to improve things is to get data you don't already have. There's a few tricks that you can, get maybe like a 5% improvement here and there, but the more, like once you start getting a certain level of accuracy, you'll notice that for the amount of work you put in, you start getting diminishing returns. All right, so that gives us an idea on the learning curve for sample size. The larger the sample size, the better the sample represents the population, the better my model will perform when I start making real predictions on it. Now let's look at complexity. Now this one's going to be a little bit more complex. Haha. Yeah, I know, it's surprising. Complexity would be a more complicated topic. All right, what we want to do now, we want to take a look at how does the complexity parameter influence the learning of our model. So let's go ahead and run the code. So once again, we're going to run through a whole bunch of models. We're going to do this over and over and over with different complexity levels. So we're generating our data. Here is our predictor variables. Here are our dependent variables. We're permuting the data, shuffling it to make sure that there's no hidden trends in there. And then we're splitting the data. So here I'm making my X test set, my Y test set. Down here, I take the non-test data and put it into the training data. Now here, we're going to create a decision tree. And you'll notice that this time, data size is the same every single time. If you dig through this ugly code, you'll notice that max n stays the same every single time. This time, the depth of the model is changing. So it's going through a range of values. And then we fit the model. And then we check to see how well does our model perform on the training data and the tested data. All right, let's take a look. Okay, so here, let's see. Well, let's do this again. All right, so actually so here I misspoke. So here what we're doing is we're saying C equals to 1. And so here, this is a very shallow tree. And we can see, so I misspoke, I jumped the gun, I was really excited. So I'm doing another decision tree, but this time max depth is gonna be 1 every single time. And we can see that with this, I've got about a 33%, about 1/3 error rate is kind of like the long term. Previously, with a deeper tree, we were able to get about 10% accuracy, or 10% error rate. Now the error rate is 1/3 because the model has a max depth of 1, which means it can't really fit the data that well. I'm not allowing it to get all crazy. Okay, well let's do something else. Let's do max depth of 20. Let's see what happens this time. Let's see. All right, let's see here. All right, with 20, it's a much deeper tree. All right, there we go. All right, so now we can see that here I was able to, I made a much deeper tree. It's a much more complicated model. And you can see that thing just absolutely fit tightly to the training data. Like boom, on the training data, it is a perfect model. It went deep, it got going, and ignore this legend. That legend's wrong. All right, so, but what happened to the accuracy on the test set? On the test set here, the error rate is actually worse than it was before. So what happened was we got nearly perfect training data statistics. And our test data statistics ended up being absolute junk, absolute crap. And so what happened? We went from about 11% to maybe 17%, 16%, something like that. All right, well, it overfitted the model. All right, the model fitted so tightly to the training data that it detected the difference between the sample and the population. And so that's called overfitting the model. If the model fits to the sample substantially better than it fits to the population, that's called overfitting. And you see that there's a wide gap. When we see a wide gap between our training statistic and our test statistic, that's when we go, whoa, 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 we overfit, back up, back off, back off, back off. Okay. So let me change this code back to where it was of 1. And I'm going to rebuild this. This will be pretty quick since the models are pretty simple. If I was editing the videos, I would just like, you know, fast forward this, but I don't have the software and I should probably get it. And now let's take a look. All right, boom, we got it. All right, so here we go. We have them together. Oops, that's not what I wanted. I wanted. Oh, it really does not want to overwrite. Okay, I'm just gonna move on. So here we can see comparatively how the models are performing. That we suffered because we increased the complexity. All right, so now let's go ahead and make things a little bit more interesting. In this case, what we want to do is we want to check to see what happens when we're changing the complexity this time. So we're going to change the complexity with each iteration. And we're going to do pretty much the same thing in my model, except this time you'll see that this loop is over the complexity parameter, the depth of the tree, not over the sample size. All right, this is probably the most important picture in all of machine learning. This picture right here. Okay, if you want to understand machine learning, you have to understand this one picture. What's going on is this, we can see that as the complexity gets going, so here, the model really is not fitting very well to the sample. It's not fitting to the population. Here, it's fitting much better to the sample and the population. Here, it's fitting to the sample and the population. Goes along, it reaches like a certain, so it's going, and you kind of have to look at simultaneously the red and the blue. It's coming down, it's fitting. As we increase the complexity, it's getting better, it's better. At the lowest point of the testing curve, the red curve, at the lowest point of the testing curve, when it's closest to the blue curve, it is fitting at its best performance to the training set and the test set. So fitting to the sample is the same as fitting to the population, approximately, at this point. This vertical point, so let's say 2.7, about 2.7. Now, watch what happens once the complexity gets bigger than 2.7. Well, once the complexity is bigger than 2.7, the training error just freaking goes downhill. It goes all the way down. It's gone, baby, gone. But what happens to the test set? It starts getting bigger and bigger and bigger. All right, so the training error, that indicates how well the model fit to the data. The test error is our indication of how well the model fitted to the population. There's two differences. And what do we see? We see that they start to spread out. So something that we need to do when we start doing modeling, we want to figure out what is the optimal value of the complexity. Usually when it comes to data, what we have is what we get. If we're in the situation where we get like diminishing returns on sample size and I have large sample, I could subsample my data to make things run faster. That's a possibility. I usually don't for my work because sample size is not an issue, but I have done it in the past. But we can see, all right, so let's go ahead and call that maybe 3. All right, so here, so we can see that everything was the best for a sample size of 3 for this data set. And then once we got bigger than 3, we started getting worse results because we don't care about fitting on the sample. We care about fitting on the population. And that's where the red curve is. So whenever I look at my statistics or my metrics for the fit of my model, I need to compare these two. If I see that they're close, I'm very happy, very comfortable with the model not being overfitted. But if I see that they're farther apart than I feel comfortable with, then I have to go, whoa, back up, figure out what's going on. What did you do wrong? All right, and that's all I've got for learning curves right now. Please take a good hard look at this one picture. This is really critical for understanding machine learning. This is this picture, this concept. I'm trying to get this into your head so that down the road, when you start making predictive models, you don't get smacked in the face, by overfitting on your data. Take care and goodbye.